So in these set of videos, I'm about to discuss solving systems of differential equations. You have seen systems of differential equations in other sections. In Chapter 8, we'll talk about a new method for solving these. So for solving a linear system, recall that a system of differential equations, you will have a collection of differential equations. We will focus on linear systems, so each of those differential equations will be linear in terms of the variables, and often may have this form. So this would be a 2 by 2 system. You have two unknowns and two equations. Now we can denote this system just as you would have in algebra. You wouldn't have had derivatives, but here you might use, so we use a capital X. Sometimes you'll see X with bars on it. That denotes the vector containing the derivatives of each of your variables. Notice that X and Y are both dependent on t here, so it's reminding you of parameterization from Cal 3 perhaps. On the right, the coefficient matrix A, so that represents a 2 by 2 matrix made of the coefficients of each of your variables on the right, and X represents the vector containing the two variables. Notice that in such a system, the origin 0, 0, so when x is equal to 0 and y is equal to 0, that will always be an equilibrium point for the linear system. What we want to do is find non-zero solutions. So we intend to generate solutions which will represent all other solutions to that system of differential equations. Now to do this, or to consider what types of solutions we might have, I want you to make this one assumption, so we'll talk about this. I have a scalar lambda here, so just a real number times a vector v. Now v, we'll discuss that later. So what this is saying is you have scalar multiplication on the left is equal to this product. This is product of matrices. So A here is your coefficient matrix I discussed earlier. V is a new vector I'm introducing, and lambda is a new scalar I'm introducing. So what I want you to assume, so based on this assumption, we're saying that lambda, a scalar multiple of some vector v, is equal to our coefficient matrix times that vector v. The size of A and V will be determined by your system. They must be the same size, so the size of V is predetermined by how the dimensions of your coefficient matrix are developed from your differential equation. Once you've made this assumption, so this would imply that x is equal to e to the lambda t times vector v. Now why are we saying this? So to clarify my explanation, from previous sections when you had a differential equation, so this goes back to chapter 1, when you had a differential equation, x prime was equal to a constant multiple, times that exact same variable. Then solutions had the form of exponentials times constants. So what we're saying here is we're going to assume, because that differential equation has that form, that we have matrices solutions of the form of that variable equivalent to a constant multiple. So kind of think of v, it's going to contain constant multiples of exponentials. So that is where we're headed right now. So x equals e to lambda t times v we're going to assume that it has this form because of the setup of the differential equation. The same reasoning we used in chapter 1 and 2. If we make those assumptions, so again, those are all of our assumptions, then notice that x is indeed a solution. And so if you plug in this purple portion right here, x prime would be lambda e to the lambda t times v. V contains constants. It is a vector containing constants. Then I've rewritten this, so I've pulled out the e to the lambda t, and this would be a scalar product here. So I have a scalar times a vector. These are all, so this is just a vector containing constants. Now based on my assumption up here, we're going to assume that lambda v is equal to a times v. So I've substituted that back in. If that is true, then you'll notice I have a e to the lambda t v here, which is x, so that I have ax. What this is saying is I ask you to make some assumptions. Based on those assumptions, you're able to see that those assumptions would guarantee a solution to such a differential equation. The idea we're developing here is solutions for such systems, linear systems, will have this form. So solutions will have the form that x is equal to e to the lambda t times a vector filled with constants. Now we're about to talk more about lambda and v, but this is to develop that idea. All of your solutions, so anything in your solution set, will have this form. X of t is equal to e to the lambda t times a vector. Based on that assumption, so solutions will all have this form, lambda, so you'll have, for however, depending on the dimensions of your matrix, then you'll have this similar number of solutions for lambda here, or similar number of eigenvalues. So lambda, each lambda is called an eigenvalue. So it's a new vocabulary word. And each vector, which corresponds to that eigenvalue, is called an eigenvector. So eigenvalues and eigenvectors will be what we're solving for in this section in order to write our solution sets, which appear in this form. How do we find those? Based on our assumption, again, that was all things to lead you to help you understand why they have this form. So based on that assumption, you'll notice this scalar product equal to a matrix product. If I put those on the same side, so because this is a scalar product, we multiply that scalar times I here so that we can factor out v. So what this is saying is you have to multiply that scalar times a matrix in order to write the multiplication in this form. And what we have then is a matrix, so this difference of two matrices on the left, so A minus lambda I. That's the identity matrix with lambda down the main diagonal. We have that product times a vector. This vector is going to be our eigenvector. And because that product is equal to the zero vector, so the vector with zeros down the column, we want non-zero solutions. And so what we'll be doing then is we need to solve for any non-zero solutions, which will only appear if the determinant of this is equal to 0. We don't want v to be a vector with zeros down. That wouldn't help us solve for any non-zero solutions. So we want to find when the determinant of this matrix, this difference right here, is equal to 0. This equation then, so the determinant of that equal to 0, is called our characteristic equation. This, and often I would use the word characteristic equation accidentally in some of our old chapters when we were using the word auxiliary. So the characteristic equation, though it's the exact same idea as what we were doing in chapter 4, it's just using matrices. So here we're going to be taking the determinant of that difference and solving for when it's equal to 0. We will have, for a 2 by 2 system, 2 solutions, and so we'll have 2 different eigenvalues and 2 different associated eigenvectors. And so that's what this is just saying. For a coefficient matrix, we'll have, so for a 2 by 2 system, we will have 2 eigenvalues and 2 eigenvectors. Now, solutions will have this form then, so each of these would be in our solution set. We'll have a constant multiple of e to the lambda 1 t times the vector, the eigenvector associated with that. And similarly, for your second eigenvalue, you'll have a second eigenvector associated with that. This will be the form of our solution set then. Notice that this is a vector, so x of t, y of t. This contains x of t, y of t, c1 e to the lambda t times a vector, so this will contain 2 constants and 2 constants. So really, these solution sets, when it's written in this form, it's the exact same as what we were doing in chapter 4. It's just writing it in form of vectors, and that's all that's new.